Hello, everybody. Another reminder, there's no fourth week video, or at least last week of the month video. If I do, it's going to be on my personal vlog, Genesis Ong. Otherwise, this series is everyone joining me to watch systems thinking videos, or at least the introduction to the entire paradigm, the way of thinking. And if you've watched my last two videos so far, you'll see that we've touched on several videos with animations and very individual, unique case studies and examples that really try to frame systems thinking in as many ways as possible, with, for the most part, showcasing that it is a way of thinking with relationships rather than the objects or the elements themselves. So right now we're about to dive into Systems Thinking 101 from Furman University, which I believe is in South Carolina. Anna Justice is the speaker for this one. Let's get this going. All right, let's go. It's a bit longer. That's why I'm only going to play one video this time instead of two.
Hello. Welcome to Systems Thinking 101.
Great.
When I tell people I am a sustainability science major, I am often met with a head nod, followed by a, wait, what's that? Now, most people understand sustainability as sustainable development. And in sustainable development, we are looking at how we can meet the needs of present generations without compromising the ability for future generations to meet their needs.
Okay.
Now, today I am just going to focus on one aspect of what I have learned and applied to my daily life, and that is systems thinking.
Yep. Daily life systems thinking.
Well, systems thinking is an integrative way to view a large and complex issue as part of a group or system of elements together as a whole.
Nice.
Systems thinking requires you to take a step back and look at the big picture. To understand systems thinking, you first need to understand systems. To understand systems thinking, you first need to understand systems. Now, systems refers to how elements interconnect and work together to form a unified whole. Examples of systems include the human body. The human body has a set of DNA, tissues, cells, muscles.
Right.
And
Organics
they all
are
rely on one
often,
another to
biology is
function
often the
correctly.
easiest way to explain it.
A forest is an example of a system.
Right.
It has plants, animals, soil, water, all to produce that specific type of landscape. An economy is a system.
I
It
like how
has a
she's
set of rules,
going from smaller
behaviors,
to scaling
and
outward.
institutions that govern how our society should exchange goods and services. Now, systems can also exist within systems. For example, a city is a larger system that could be broken down into smaller systems,
Right.
such as local government, hospitals, schools, businesses, residents, and so on. Now, there are two key takeaways here. Systems are everywhere,
Yep.
and they exist at various scales.
Exactly.
Now, systems have inputs and outputs.
Yep.
In linear thinking, we can easily see that input A
Love it.
affects B, which affects C, which affects D. And D is that final output. Since we can more easily process this and identify the cause and effect or causal relationship, we are more prone to be linear thinkers. Now, what if outputs were also inputs in the same system, or another one?
Yep.
Well, then we'd get something like this. You might be wondering, where does it begin?
Double loop diagrams like this, or double loop is like a helix, but this is like, it's showing that B goes to D, E, and then C. When I was doing a sustainability certification over at MIT, we dealt with a kind of almost like a parasitic or a secondary loop like this. And it's a great way to really expand the fact that this isn't just a circular, this is not just a singular cycle. There is more to it.
Where does it end? Well, unlike linear thinking and circular thinking, there is no specified end. You can see that there is continuous feedback among each element.
Yep.
In the examples we are going through today, we will be creating these loops and identifying causal relationships. And we are going to constantly be asking these two questions. How are the elements interacting, or the system dynamics? And what is the goal of the system, or the desired output? A great way to begin systems mapping is through the iceberg model. The iceberg model reminds us that what we initially see on the surface isn't going to tell the whole story.
Yep.
Now at the top we have event. The second layer is patterns, and if you view that event over time, you can maybe identify patterns. The third layer is structure, and structure refers to systemic structures. Now, let's say I bought a shirt last week, and I bought it because it was trendy, it was at a good price. Well, if we view this at the top layer, there's not much else to it. But let's move to the second layer. At the second layer, we could discuss how this shirt in a year, or maybe even a few months, will no longer be trendy. And then I might buy a new shirt. And then that's going to repeat and generate a pattern. The third level is where we perform systems thinking. Now we are going to use a causal loop diagram. A causal loop diagram is a visual aid to show how elements in a system are interrelated, and we are going to use words and arrows. You can think of it like systems thinking art class.
Yeah, it's kind of weird. I almost feel like she's talking to an empty audience chamber. I got that weird sense.
Now, while we started with me buying a new shirt, we're going to take a step back and get a bit broader. And we're going to identify the overarching system as the clothing industry and focus on a clothing company. Now we need to identify the inputs and how they interact in the system. So the clothing company has identified demand. There's demand for clothes. And they have also found that customers will buy clothes if they're cheaper. So then we move to production. The clothing company will make clothes cheaply by outsourcing labor and using cheaper materials. This creates a lot of inventory. And in that inventory, they want to sell it as much as they can so they can keep creating new products, because new products increase customer attractiveness. So this will increase marketing. As marketing increases, so does the number of customers that buy clothes. This generates profit. And profit is a signal to the clothing company to keep making more clothes. So we can draw an arrow straight back to production. Now, if you can see the little plus signs next to each arrow, that indicates positive reinforcement, or an increase. Now, while there are more variables in real life to complete this process, for the sake of today's exercise, we want to keep it simple. Let's make another causal loop diagram. We are going to stay within the same system, the clothing industry. But we are going to build off customers. So the customer buys clothes and then receives the clothes. What's next? Well, we assume the customer is going to wear those clothes. So this increases the clothing use over time. And as clothes are more used, they have an increased chance of wearing out or going out of style. And that's going to indicate to the customer to throw away the clothes or donate them. And both of those options inevitably end up at a landfill. Now, wait a minute. This doesn't look the same as our first example.
Correct.
That's okay. In systems thinking, it can sometimes be hard to figure out that connecting arrow, or what's going to connect the loop.
I love causal loop diagrams. It's one of my favorites because I'm a visual, I just love diagrams in general. And what she's pointing out is a great way to understand the fashion industry as it is today and how it's generating so much waste. If you've seen some of my past videos, especially the one where I touch on Ghana's intake of used clothing, that's just an extension of what she's laying out here with the landfill example.
Can you see where we could draw an arrow from one of the variables back to customer? Now, technically, you can make a case for any of those first three variables, but I'm going to add an arrow from throwing away or donating clothes back to customer. Because typically, when we get rid of clothes, we go and buy more, and that makes us a customer again for that clothing company. Now, let's take this example and connect it back to our first example. Well, then we get something like this. Whoa. Now, looks complicated, but guess what? You can now walk someone through this.
And this is not an absolute. This is just a version of a diagram that she's charted. Depending on who's designing the causal loop diagram, you can make an argument and association that ties in other factors and other stages in the causal loop diagram, which may yield different outcomes. So just wanted to point that out.
And if you're wondering what this is, well, you just use systems thinking to break down the complex issue of fast fashion. Now, fast fashion is a term
Horrible.
to clothing industries that use this type of production to produce affordable clothes through the use of cheap materials. And what that means is there's a trade-off by having decreased clothing quality. By using cheaper materials, these clothes break down faster, and they're much harder to recycle. Therefore, we get a lot of clothing waste in landfills. Now, this is an undesirable result in the system, but the clothing company is still meeting their desired output to make profit by selling clothes. Let's walk through another example. This time we're going to look at industrial agriculture.
Oof.
Now, a bit of background is the goal of industrial agriculture is to grow food. It's to meet growing population demand.
Yep.
Now, in large-scale industrial agriculture, they use chemical fertilizers.
Yep.
Fertilizers are nutrients added to plants and crops to make them grow faster, bigger, and produce more food in a limited space. However, chemical fertilizers, in contrast to natural fertilizers, are more potent. So what happens is they are added in excess, meaning we are adding more nutrients than that plant or soil needs. Mm-hmm. And this leads to soil degradation. That soil becomes more acidic, it becomes less porous, meaning it cannot hold as much water. So now let's try to map this out using a causal loop diagram.
Yep.
So we have identified demand. There are people we need to feed. And so this is going to increase the use of chemical fertilizers. Now, what do chemical fertilizers do? Well, they increase the amount of food that we grow and harvest, or crop yield. Now, crop yield, that is our desired output. So we can draw an arrow back to use of chemical fertilizers. The increase in crop yield signals to the farm to continue the use of chemical fertilizers. Now, technically, this loop is complete, but it doesn't tell the whole story of this system.
Correct.
What did we discover about the use of chemical fertilizers?
It impacts other ecologies.
I'm going to draw an arrow from use of chemical fertilizers to a new variable, soil quality. We put a minus sign by this arrow to show a negative effect or a decrease. And
I got confused with this also. Those plus and negatives are not like positive as increase and negative as decrease. Positive means, I'm going to get this wrong, I think, because I haven't reviewed this. I haven't done a causal loop diagram in a while. One is sustain and one means change. So you're dealing with a continuation or a maintenance of a flow. And another is a change in things. She's probably going to cover how things need to have both. If you have too much of one, it's an imbalanced loop.
if the use of chemical fertilizers is lessening the soil quality, this then lessens the crop yield because crops cannot grow as well in poor soil. Do you see a conundrum in this system? We'd expect that a decrease in soil quality would signal the farm to use less chemical fertilizers, but it actually increases the need. Why is that? Well, remember, the desired output for this system is food. So their focus is growing more food. So if they see that soil is struggling and so are the crops, they're just going to add more fertilizer. And what can happen over time is as that soil keeps degrading, it can be more easily carried away by wind or washed away by water. And what that means is someday in the future, we might not have soil to plant crops in. Now, I'm going to stop there.
So, again, that diagram, that negative by soil quality is not that it's that negative defines that the quality's gone down. It's the fact that the introduction of the contaminant is changing the soil quality, and it's doing so in a way that is not promoting the quality of just what it's intended to do in the long term.
This is one of my favorite systems examples because while it looks deceivingly simple, it has huge implications for so many other systems to be able to function. Now today we use systems thinking to look at the system dynamics of fast fashion and industrial agriculture. In both systems, we saw undesirable results: clothing waste in landfills and soil quality going down. Now, systems are not inherently right or wrong. They have developed over time based on our values and beliefs. And ultimately, as these systems developed, they weren't aware that they might be creating a problem in another system. And systems come with surprises and unintended consequences. The next step is what my major is about: solutions thinking. We are looking at where we could intervene and change the system. This is the equivalent of adding a new arrow or variable.
Systems intervention.
And we hope that we could somehow mitigate any unwanted outputs. Could we have a clothing system where clothes are never sent to a landfill and are recycled back into production? Can we grow enough food to meet current demand while letting our soil rebuild at the same time? My hope for you today is not to solve either of these problems. They are very complex, and there is no one solution. My hope is that you can see the effectiveness of systems thinking and identifying connections and understanding why any system behaves the way it does. What I love about systems thinking is how it has changed my perspective. I see the world differently now because I can identify these connections more easily, and I can see the subsequent impacts they have even when it is no longer directly impacting me. When I make decisions, I can see that I play a part in...
All right, this is bugging me. I need to figure out for flow diagram systems symbols. No. Not a flow diagram. Causal loop diagram symbols. Yeah, so there's also delays. So let's look at this real quick, because I really need to have this clarified, because I don't do it enough. Okay, yeah. So it's not that positive means more and negative means less. We have to think of it from a physics standpoint. It's polarities. So a plus means that it's going to continue building, whereas a negative, it's switching polarity, so it's going in reverse, or it's going counter. It's going counter to the promotion of the other pattern. So when she's looking at like soil quality, the soil quality is technically, she's right. Technically, it is going poorer because it's going opposite of the other side of the flow. I mean, let's go back into it, because this is, my explanation is horrible. So demand is there, increased demand, use of chemical fertilizer is increasing, and then the crop yield is increasing. But in counter to that, the soil quality is degrading. But that is not indicated by it showing negative. It just means that it's going the opposite direction. So, for example, let's say this plus means that, you know, it's putting in less chemical fertilizer. And then, or using, let's say, weed killer. So let's say we use weed killer instead of this chemical fertilizer, which kills the weeds. And then, in essence, the soil quality, let's say there's nutrients in it, if it has negative there, it's helping soil quality increase. So these are purely polarities. They don't mean more or less. It's just progressing and counter progressing flows. Let's get back into it. I'm getting too complicated.
No longer directly impacting me. When I make decisions, I can see that I play a part into larger systems. By using systems thinking to understand how a system is achieving its desired results, I can make better informed decisions based on my own individual values. I hope I have inspired you to incorporate more systems thinking into your life.
There really is
and
no
if you're
one
still
there.
unsure where to start,
Interesting.
ask questions. Have a curiosity to think deeper. Ask those questions that are going to make you take a step back and look at the big picture. So the next time you're shopping for clothes, or buying produce from a grocery store, or even throw something in the trash can, I want you to think of all the steps that item went through to get into your hands. And then I challenge you to also think of all the steps that item will go through once it leaves your hands. Remember that systems are everywhere, and you are part of these systems. You have an impact, therefore your actions matter. Thank you for coming to my TED Talk.
Nice. Not bad. It's interesting how that TED Talk inspired me to look up causal loop diagram symbols again, because it's the last time I did it was purely for MIT early last year. So coming back to it again, it's good to have a refresher, especially with something as complex but meaningful as systems thinking. Thank you for watching along with me. Look forward to more videos in this series of watching along and learning more about systems thinking. And thank you for watching, and I'll catch you guys later.